The ocean is stealing Earth's oxygen, and we can't stop it. The fish weren't dying quietly. By sunrise, the bay looked like a silver blanket. Thousands of bodies surfacing at once, gills flared, mouths locked open. The oxygen was gone. Crews waded in with nets, moving as if the water itself were heavy. Here's the twist. While we breathe easy on land, the ocean, the source of roughly every second breath, has started to suffocate. Dead zones are spreading where life should explode. Storms ride warmer seas, but it's the missing oxygen that turns abundance into silence. The engine that helps make our air, tiny green drifters, has begun to glitch. Stick with this, because somewhere in this story is your local bay, your dinner, your job, and your next breath. To understand why, we rewind to the microbes. Roadmap of Revelations. We're going to follow the ocean's breath and watch where it falters. First, we start at the climax, mass fish kills. Then pull the camera down to the smallest workers in Earth's life support system, phytoplankton. They're microscopic, but their job is massive, pumping out about half of the planet's oxygen and feeding almost everything that swims. Then we meet the physics. Warm water holds less oxygen. It sounds simple, and it is. Brutal, too. As the surface heats, the ocean stratifies into layers that don't mix. Oxygen gets trapped near the top, while the deep gets starved. Meanwhile, nights, heat waves, and calm spells tip local ecosystems over the edge. But biology and human choices push harder. Fertilizer and sewage spark blooms that crash and rot, and microbes claim whatever oxygen is left. The villains you rarely see. Stratification, nutrients, timing work together. We'll test the decline signal. Satellites reading chlorophyll, ships dragging sensors, and decades of buoy records. We'll weigh conflicting datasets and show where the trend is real. Losses in the nutrient-poor tropics, shifts at the poles, noisy coasts, and we'll anchor it with numbers, like the roughly 0.5 to 3.3% loss of oxygen from the upper ocean since about 1970, and the expansion of the world's low oxygen zones. We'll track the slow creep of deoxygenation offshore, the rise of oxygen minimum zones, and the squeeze on fish between heat above and breathlessness below. Then we'll stack the tag team of acidification and low oxygen, where stress multiplies. Finally, we'll put we can fix it on the table. What works locally, what doesn't scale, and what the physics demands. In-game question. If the ocean can't exhale like it used to, what happens to ours? The breath makers. Phytoplankton 101. To understand the ocean's breath, we need to meet the ones doing the breathing in reverse. Phytoplankton are the ocean's tiny solar panels, single-celled drifters, some with glassy shells, some with elegant whips, all turning sunlight, water, and dissolved carbon dioxide into sugars. The byproduct: oxygen. They do it by the billion, every second, across most of the sunlit sea. Think of photosynthesis like a savings account. Light deposits, energy, carbon becomes stored chemical money, oxygen is the receipt. Meanwhile, everything else, from zooplankton to tuna, makes withdrawals. Balance is everything. When the deposits shrink or the withdrawals spike, oxygen goes missing. Phytoplankton don't bloom on a whim. They live by a global heartbeat. In spring at high latitudes, storm-mixed waters settle, light floods the surface, and nutrients left over from winter mixing are right there. A population explodes so fast you can see the color from space. A green smear off Newfoundland, a turquoise spiral in the Southern Ocean. Then grazers catch up, nutrients thin, and the pulse fades. In subtropical gyres, the big blue deserts, light is abundant, but nutrients are locked below the thermocline. Here, the heartbeat is faint. Small cells with efficient machinery dominate, living close to the edge, recycling every atom of nitrogen and phosphorus they can find. Upwelling coasts are the opposite. Winds lift cold, nutrient-rich water, and blooms roar to life. These regions feed the world. 3 throttles control the show: light, nutrients, and iron. Light is obvious. Nights and seasons write the rhythm. Nutrients, especially nitrogen and phosphorus, set the growth ceiling. Iron is the secret lever. In parts of the ocean where dust is scarce, like the Southern Ocean and the North Pacific, iron starves phytoplankton, even when other nutrients are plentiful. A whiff of Saharan dust can flip a patch of sea from quiet to vibrant. Micro-story. A fisherman from Galicia holds a weathered notebook. For 30 years, he scribbled the dates when water shifts from slate to green, when sardines move in, when the squid lines go heavy. He circles a weakened May that used to be reliable, then sighs. Lately, the bloom comes early, or late, or not at all. Timing isn't a detail. Larval fish hatch on a schedule. If the bloom peaks before mouths are ready or after the nursery window closes, survival. Nosedives. The match between bloom and nursery time is a hinge for whole fisheries. Phytoplankton are also engineers of climate. They pull CO2 from surface waters and, through grazing and death, send some of that carbon downward in sinking particles. This biological pump doesn't just store carbon, it helps keep surface waters undersaturated with CO2, letting the ocean absorb more from the air. The oxygen they release mixes into the top layer, then rides currents and winter storms downward, ventilating the depths. Here's the catch. Phytoplankton breathe too. At night, and in the dark ocean below, respiration runs the other way, consuming oxygen. When organic matter rains down, microbes throw a feast, and the oxygen tab rises. Usually, mixing and winter ventilation settle the account, but warm water changes the math. Warmer surface layers hold less oxygen to begin with. They also sit on top of cooler, denser water like oil on vinegar. The seasonal lid, stratification, thickens and the stirring weakens. Oxygen can't easily move down. Nutrients can't easily move up. The photosynthetic deposits shrink. The respiratory withdrawals don't. The account trends negative. Meanwhile, on coasts, we keep feeding the system. Fertilizer and sewage load rivers with nitrogen and phosphorus. Blooms explode, then crash, and the microbial cleanup pulls oxygen towards zero. Add a heat wave, a few windless days, and a spring tide, and you get the silver blanket at sunrise. Stakes? Remove this layer, and food webs stall. Zooplankton lose their base. Forage fish go hungry. Predators chase dwindling bands of survivable water. The biological pump weakens, meaning more CO2 stays near the surface and in the air. The ocean's exhale becomes erratic. Translation, empty nets, volatile prices, failed seabird nests, and a climate that pushes harder next year. A scene from orbit. A satellite pass catches a filament of bloom unspooling off Peru, neon turquoise twisting into cobalt. To the eye, it's gorgeous. To the fleet waiting 12 miles offshore, it's a calendar. They know a few days later, anchovies will ride the edge of that color line, feeding on the plankton wave, unless the wave breaks wrong. And here's where it pivots. Signs point to a world where those tiny solar panels are shifting, towards smaller cells, earlier pulses, longer lulls in some regions, and more violent swings in others. The heartbeat is still there, but the rhythm is changing. If these breath makers power half our oxygen, directly and by setting ocean chemistry, then a slowdown, a mistimed pulse, or a chaotic swing doesn't stay at sea. It follows the currents into food, economies, and yes, the air we share. So if they help decide our breath, why are they fading? To find that answer, we leave biology's engine room and step into the ocean's physics. The decline signal, are phytoplankton actually dropping? To see if the ocean's breath is thinning, we need receipts. The first come from space. Since the late 1990s, satellites have watched the ocean's color shift day by day. Chlorophyll, the pigment that makes phytoplankton green, tints the sea. When it brightens, blooms are likely. When it fades, productivity often falls. It isn't perfect. Color can lie when sediments or dissolved organics muddy the view. But stitched over decades, the trend lines matter. Vast swaths of low-latitude oceans are getting bluer, not greener. On deck, ships drag sensors through the surface and into the dim fluorometers, sniff chlorophyll. Bottles grab water for lab analysis. Nets catch the cells themselves. These transects don't cover every ocean mile, but they give truth to the pixels. Floats and gliders add the slow, patient heartbeat. Profiles every 10 days, year after year, even in winter storms when ships stay home. Together, it's a triangulation. Eyes in orbit, hands on railings, robots in the dark. So what do they show? In the tropics, where nutrients are chronically scarce, chlorophyll and net primary production have sagged. Warmer, more stratified surfaces mean fewer nutrient injections from below. In the wide subtropical gyres, the desert is expanding. The bluest blues are spreading. Farther poleward, the story tilts. Spring blooms still fire, but timing drifts and community makeup leans smaller. In some subpolar regions, total production hasn't collapsed, but the cast has changed. Tiny picoplankton shoulder more of the work, while big diatoms lose ground. Coasts are noisy by design. Upwelling years punch chlorophyll sky high. El Niño years flatten it. River plumes feed bursts of green that can be food bonanzas or set the table for dead zones. The datasets here fight each other. Some years look like recovery, others like freefall. That's the point. Variability is rising. Fishermen feel it in shorter, sharper seasons and longer, emptier lulls. The Gulf of Mexico's seasonal dead zone, for instance, can sprawl thousands of square miles in midsummer, waxing and waning with spring runoff and heat. Now the caveats, because this isn't a courtroom drama with one exhibit. Satellites see only the top layer and infer chlorophyll from color using algorithms that can drift over time. Instruments age, calibrations shift, atmospheric dust throws off the math. Even the definition of trend depends on which years you choose. Early studies flag global declines. Later reanalyses softened that to regionally mixed with deserts growing. But independent lines keep pointing the same way in warm, stratifying waters. Less nutrient supply, smaller cells, lower net production. Lab cultures add a different lens. Warm a diverse plankton community, and you don't just speed things up, you change who wins. Many large silica shell diatoms run into nutrient stress sooner. Small cyanobacteria hold their ground. Diversity drops, and with it, resilience. That's not a global ocean in a beaker, but it echoes what ships and satellites report. Here's where the signal touches dinner plates. In systems like the California Current and the Humboldt, years with weaker, mistimed blooms leave anchovy and sardine recruits thin. Larval survival collapses when the plankton menu shrinks or arrives off schedule. Seabird breeding fails in lockstep. Trawlers read the echo sounder and see the squeeze. Prey fish pressed into narrow bands where temperature and oxygen still cooperate, then gone. And remember that chlorophyll isn't oxygen itself. It's a proxy for the engine that sets oxygen's budget. In nutrient-poor seas, fewer phytoplankton mean less photosynthetic oxygen added to surface waters and a weaker biological pump. In eutrophic coasts, spikes in chlorophyll can be the first step toward a crash in oxygen debt. Both ends of that spectrum can leave the water gasping for different reasons. What about counterpoints? Regions where productivity is ticked up. They exist. Melting sea ice has opened light to some polar shelves, briefly boosting blooms. Dustier skies in certain years deliver iron that wakes up high-nutrient, low-chlorophyll zones. But these are patches and pulses, not a blanket reversal. Many gains look fragile, dependent on short-lived conditions, and vulnerable to the next marine heat wave that can slash chlorophyll and reset communities towards smaller, less nutritious cells. Speaking of heat waves, the ocean's new extremes make trend detection harder and more urgent. A marine heat wave can slash chlorophyll for weeks, then the average recovers on paper while the ecosystem doesn't. Corals bleach, kelp forests shrink, the plankton community resets to smaller, less nutritious cells. The baseline ratchets even if the line looks flat. One detail will matter later. As cells get smaller, they change not just how much carbon they fix, but where it goes. Small cells tend to recycle in the surface. Their carbon lingers, feeding microbes that respire oxygen away right where stratification is strongest. Less carbon sinks, so less oxygen rides downward with ventilated waters. The oxygen account gets squeezed from both sides. Fewer deposits, harder transfers. So, are phytoplankton actually dropping? The fairest answer is, in many warm, nutrient-limited regions, yes, the desert is growing, communities are shrinking and shifting, and timing is slipping. In colder, dynamic regions, the pulse is changing in ways that can still starve nurseries and scramble food webs. On coasts, volatility is the new norm, and volatility kills predictably. We've taken the pulse of the breath makers and heard a stutter. To understand how that stutter turns into silence, the missing oxygen itself, we have to leave color and counts and step into chemistry and physics, where warm water, layers, and nights decide who breathes and who doesn't. Warm water, less oxygen, the physics that suffocates. To see how missing plankton turns into missing breath, we need the rule that never blinks. Warm water holds less oxygen. Take 2 glasses, one cold, one hot, shake in air, and measure. The cold glass stores more oxygen molecules between water molecules. Heat jostles them out. The ocean is the same glass, just bigger. As surface waters warm, they start with less oxygen to give. Now add layering. Warm water floats on colder, denser water. That top layer forms a lid, a stratified cap that resists mixing. In winter, storms and cooling punch oxygen downward, but as the climate adds heat, the lid thickens and the punches land softer. The ocean's conveyor for oxygen slows. The deep keeps breathing out carbon and using oxygen, but the resupply from above gets starved. This is where the day-night cycle becomes a gambler's coin toss. In sunlight, phytoplankton add oxygen to the surface layer. After dark, everything respiring, plankton, fish, microbes, draws oxygen down. On a hot, breathless night with no wind, that drawdown can outpace the day's deposit. By dawn, the line crosses a threshold and gills fail. A single still night doesn't cause a dead zone, but it closes the gap. Stack a heat wave, a spring tide that slacks currents, and a recent bloom, and the physics tips the biology. Mixed layers, the depth of that surface cap, are shoaling in many places. Shallower caps mean the day's oxygen stays trapped near the top centimeters, saturating quickly and bubbling back to the air instead of ventilating downward. Meanwhile, the dark waters below keep respiring. The mismatch grows. Production up top can't reach demand below. The account bleeds. Wind matters more than we like to admit. Trade winds slacken during certain climate swings, and local calms are stretching longer. Less wind means less stirring, less oxygen injection, and more time for consumption to run ahead. Marine heat waves supercharge it. Warm anomalies can raise respiration rates and lower oxygen solubility at the same time. A 1-2 hit. During the 2013 to 2015 warm blob in the Northeast Pacific, oxygen at mid-depth sagged while the surface cap hardened. Fish and crabs squeezed into ever-thinner bands. Then there's the slow creep in the open ocean. Oxygen minimum zones, natural midwater layers where oxygen runs low, are expanding and rising. The reason loops back to physics. As surface waters warm and freshen, they mix downward less. The interior receives less oxygen, but organic matter raining from above still decays, consuming what's there. Since about 1970, the upper ocean has lost on the order of 0.5 to 3.3% of its oxygen content, and the minima are thickening and shoaling toward the layers where tuna and billfish hunt. Predators get pinned between heat above and hypoxia below. Case study, quiet and devastating. A calm August week on a temperate shelf. A recent heat wave kept the mixed layer razor thin. A modest bloom flared and faded. Nights ran warm, winds slept. By the third dawn, oxygen meters on a pier ticked down to stressful levels. Crabs crawled up pilings. Eels surfaced. A gusty front finally turned the water over, rescuing the shallows while pushing low oxygen water laterally along the bottom. A mile away, a cove woke to a fish kill. Now fold in the invisible arithmetic of respiration. Warmer temperatures increase metabolic rates. The Q10 rule of thumb says many biological processes speed up with heat, often roughly doubling with a 10-degree rise. That means for the same unit of organic matter, microbes burn oxygen faster in warm water. So we start with less oxygen, mix less of it down, and use it faster. You don't need catastrophe to lose the bet, just a few percent in each factor aligned. Coral reefs know this math by feel. Heat waves push corals to bleach, expelling symbionts that feed them. Nighttime respiration in stressed reefs can pull oxygen low enough to add suffocation to heat stress, especially in enclosed lagoons. Similar spikes hit kelp forests after marine heat waves. Canopy loss slows local mixing, and decomposing detritus quietly taxes oxygen. There's a twist that looks like good news, but isn't. In shallow, sunlit waters, photosynthesis can oversaturate oxygen, briefly pushing concentrations above 100% relative to air. It sparkles as bubbles on algae. But when stratification is strong, that surplus vents back to the atmosphere instead of diving down. The deep still waits. You can see how nutrients turn this screw even tighter, but hold that thought. The physics alone, lower solubility, stronger caps, shallower mixing, faster respiration, moves coastlines and midwaters toward thresholds they used to flirt with only on rare nights. Cross them more often, and biology starts writing new rules for who lives where and when. Now add fuel, and the floor drops out. Nutrients, algae, and the nighttime heist. Here's the fuel we've been holding. Nutrients. When rivers carry fertilizer and sewage to the coast, they don't just color the water. They load it with nitrogen and phosphorus, the very throttles phytoplankton crave. Sun comes up, the lid is strong, and a bloom ignites. An emerald switch flipped across a bay, a delta, an estuary mouth. Fishermen cheer at first. Nets go heavy with grazers and baitfish, but blooms are burst by design. They peak fast, then the real heist starts at night. When the algae die or get grazed into tiny particles, microbes take the stage. Their feast is chemical, relentless, consuming organic matter, inhaling oxygen, exhaling CO2 and acids. In a stratified system, that decomposition doesn't ventilate away. It pools near the bottom, peeling oxygen off hour by hour. By the second or third calm night, hypoxia, low oxygen, arrives like a curfew. Add another day or a spring tide that slides low oxygen water sideways along the seabed and pockets tip into anoxia. No oxygen at all. Hypoxia and anoxia aren't the same neighborhood. In hypoxia, many animals still move, but sluggishly. Behavior changes first. Shrimp lift from the bottom, fish school tighter, seeking thin ribbons where they can breathe. In anoxia, movement stops. If sulfide-producing bacteria bloom, common when oxygen is gone long enough, water takes on that rotten egg smell. That's hydrogen sulfide, a toxin that shuts down respiration outright. It stains sediment black and burns gills. You don't mistake this for anything else. Now map it. The Gulf of Mexico's seasonal dead zone forms where the Mississippi delivers a continental diet of nutrients. After spring planting, rains flush fertilizer downstream. Warmth arrives, stratification locks in, and blooms flare across the shelf. Weeks later, bottom waters read like a slow-motion asphyxiation, often spreading across several thousand square miles until storms remix the layers. Shrimpers, seeing oxygen forecasts, steer for the edges, spending extra fuel to chase the surviving bands. Catches get weird. Lots one day, nothing the next, as fish slip ahead of moving fronts of bad water. Across the Atlantic, the Baltic is a different machine with similar results. Its semi-enclosed basin and limited exchange with the North Sea trap nutrients and strengthened layering, especially after mild winters. Hypoxia, there isn't just seasonal, it can persist year to year over large areas of the seafloor. Historical overfishing thinned top predators, shifting food webs toward more plankton-fueled cycles. Sewage upgrades helped in places, but legacy nutrients stored in sediments still leak back, a memory the sea won't erase quickly. The Black Sea and parts of the East China Sea tell kindred stories. Rivers, warmth, calm spells, blooms, and the same nighttime arithmetic. Micro story. A captain out of Houma, Louisiana, stares at a handheld meter. It reads 1.6 milligrams per liter, below the 2. Migden Lobre fouls indifference. It a line where his crew starts worrying. He hauls his trawl early, moves 10 miles east, checks again, 3.4. They set, pull, leapfrogging a boundary that slides under the dark like an invisible fence. Back home, his kid's soccer practice gets rained out by the same storm that finally breaks the cap and saves his week. The link runs from field to river to net to kitchen. It's tempting to call this a problem of too much algae, but the villain is timing plus stratification. The same nutrients in a windy, well-mixed system might burn through without bottom water suffocating. In a lidded system, those nutrients light a fuse, and the CO2 produced by decomposition adds a second stress, lower pH in bottom waters. Acidified low-oxygen water makes it harder for clams, oysters, and juvenile crabs to maintain shells and for fish blood to carry what little oxygen remains. That's the double hit many hatcheries learned the hard way, buffering intake water just to keep larvae alive. Zoom in further to the nightly cycle. In shallow estuaries, daytime photosynthesis can spike oxygen above 100%, giving noon a false sense of safety. After sunset, the same biomass flips, respiring alongside everything else. With a strong cap and no breeze, oxygen drops like a rock. By dawn, crabs are at the surface, their antennae breaking water, and egrets hunt fish that can't flee. One missed wind event, one extra warm night, that's the margin. Can we pull this lever back? Yes, locally. Cities that upgraded wastewater plants saw bays brighten and stay breathable longer. Wetlands stitched back into river mouths shave peaks off nutrient pulses and slow the surge. Farmers who keep cover crops and time fertilizer to plant uptake send less nitrogen downstream. These are not silver bullets, but they are breaks that work. Because here's the uncomfortable line through it all. The physics set the stage, but nutrients pack the theater. Warm water lowers the ceiling, stratification locks the doors, nighttime respiration turns off the lights. Add fertilizer and sewage, and the audience rushes in, breathes hard, and the air runs out. And that's just the coasts. Offshore, where no river pours, another kind of heist is spreading in slow motion. The silent spread. Open ocean deoxygenation. Leave the coastlines and the river plumes behind, and you'd expect the water to breathe easier. No sewage surges, no fertilizer pulses, just blue stretching to the horizon. But in the open ocean, the oxygen loss is quieter, slower, and in some ways more dangerous because it's hard to see until it's already changed the rules. Start in the tropics, where a natural feature hides in mid-water. The oxygen minimum zone, a dim band a few hundred meters down where respiration outpaces supply. It's always been there, part of the ocean's wiring. What's changing is its footprint. Argo floats, robotic drifters that profile temperature, salinity, and increasingly oxygen. Keep returning with the same story. The minimum zones are spreading and creeping upward. Repeat ship sections run the same lines every few years and find the contours drifting, like a slow tide. You only notice when you step back from the tape marks. Why up and why now? Warming surface waters mix downward less, so the oxygen they carry doesn't reach as far into the interior. Meanwhile, organic particles raining from the surface still decay, pulling oxygen out of the mid-depths. The balance that once held those layers deep and thin tips, they thicken and shoal. Climate models, built on the same physics we can measure in a glass, project more of this broader, shallower minimum zones in the tropical Pacific, Atlantic, and Indian Oceans as this century runs. Here's what that feels like to life. A yellowfin tuna hunts in the top 200 meters, tracking schools of anchoveta and squid. Above, the water is warming. Temperatures push the fish's physiology toward the red line. Below, oxygen thins. The habitable band narrows. Predators and prey get squeezed into a slimmer ribbon where heat and breath are both just tolerable, and the dance turns frantic. It's not abstract. Tag data show vertical ranges shrinking in low oxygen years, and fisheries catch rates spike along these compressed layers. Not because there's more fish, but because they're trapped. Meanwhile, the lateral spread shifts entire ecosystems. In the eastern tropical Pacific, where minimum zones are strongest, midwater shadow zones, layers so low in oxygen that most fish can't cross, are rising toward depths that overlap with longline hooks. Catches skew to species that can tolerate low oxygen, changing market supply without a single policy shift. Farther west, the line between breathable and not breathable water edges into regions that once served as refuges for juvenile stages. Larvae don't read charts, but their survival rates do. What nobody aboard those floats knew at first was how fast slow can be. Year to year, the change looks like noise. A meter here, a few micromoles per kilogram there. Stack a decade, and the contours redraw a basin. Scientists stitch together thousands of float profiles and repeat cruise lines, and notice the same thing across oceans. A background decline in oxygen content in the upper 1,000 meters on the order of 1% or 2% since the 1970s, with the minima expanding by single-digit percentages that matter because they move critical thresholds. You don't need to drain the tank, you just need to cross the line where certain metabolisms fail. There's a knock-on effect on chemistry. Low oxygen layers favor different microbial pathways. Nitrification and denitrification, the transformations of nitrogen between forms, shift gears, altering how much fixed nitrogen remains for surface productivity when waters eventually upwell. In some pockets, microbes even produce nitrous oxide, a potent greenhouse gas, more readily under low oxygen conditions. That means deoxygenation can feed back to climate, which then feeds back to deoxygenation. Not a runaway, but a stubborn loop. Micro story. On a research vessel off Costa Rica, a grad student lowers a sensing package at dusk. The oxygen sensor flattens at values so low, her advisor calls them near zero with optimism. When they pull the rosette up, bottles from 400 meters smell faintly of sulfide. Not the coastal rotten egg punch, but a hint that anaerobic processes are brushing the edge. She writes, "shadow brightening" in her notebook, a private joke about how something unseen is defining the night. The squeeze doesn't hit every species the same. Some jellies thrive, their simple bodies and low oxygen demands, turning the midwater into a jelly highway. Small, low oxygen tolerant fish like lanternfish retreat into the minima during the day and ascend at night, but the ascent gets riskier as the layer rises into brighter, warmer waters. Seabirds that rely on prey making that nightly commute find emptier tables when the commute shortens or stalls. Models amplify the map forward. As the tropics widen with warming, the regions underlain by minimum zones widen too. Overturning circulation shifts, especially in the Pacific, alter the renewal rate of oxygen to the interior. The pattern is uneven. Some basins show patches of recovery as winds and currents pulse. But the baseline trend is toward thinner oxygen safety margins in the very bands where global fisheries draw heavily. Then there's the human layer. Fishers chasing tuna are already reading oxygen forecasts the way they read temperature charts, learning that a red patch for low oxygen can corral fish like a virtual fence. Managers face quotas that don't account for habitat compression, and bycatch jumps where species overlap more tightly. Insurance models for fleets don't price in the new volatility of where fishable water will be next month. Here's the quiet part, with loud consequences. Open ocean deoxygenation doesn't announce itself with floating carcasses. It redraws invisible lines, pushes species into new corridors, and rewrites biogeochemical budgets that eventually touch nutrient supply back at the surface. By the time a policy hears it, the layer has already moved. The ocean's breath is slipping into places we rarely look, and everything that depends on the middle of the sea is learning to live inside a narrowing band. Food web Jenga, when layers stop talking. When oxygen lines shift and the mixed layer stops talking to the deep, the first pieces to wobble are microscopic. Communities tilt towards smaller phytoplankton, picoplankton, and tiny flagellates that thrive in warm, stratified water. They're efficient at surviving, not at feeding the ladder above them. Zooplankton that once grazed chunky diatoms now pick at finer fare, burning more energy per bite and passing less nutrition up. It's like replacing loaves with crumbs. You can still eat, but you can't build muscle. Jellyfish notice opportunities faster than fish do. Their bodies tolerate low oxygen. Their prey, eggs, larvae, and small zooplankton don't escape as quickly. In arenas where oxygen bands pinch predators and prey into the same strip, jellies bloom. Nets haul up translucent bells instead of baitfish. Energy that used to sprint through anchovies into tuna now loops through gelatinous zooplankton, returning to microbes when jellies die and sink slowly, smearing decay through the oxygen minimum rather than exporting clean pellets that drop fast to the deep. Larval fish live or die in microclimates. They hatch into layers with the right temperature, prey size, and oxygen. Shave a few milligrams of oxygen from that layer or slide it 10 meters shallower into brighter, hotter water and the nursery shrinks. The larva must swim farther for meals, burn more, grow slower, and hit the predation window longer. A week of misfit conditions can erase a year class. Managers feel it 2 years later when a cohort never shows in the survey and the quota math tightens. Micro story. Off Namibia, a sardine school once broke the surface so often that seabirds nested on a schedule. Then, in a span of seasons, sardines crashed and jellyfish surged. A deckhand kept a tally in chalk on the rail. Crates of fish one year, then buckets of jellies the next, then mostly nothing. The birds tried to switch to anchovies. That worked until oxygen shoaled again, compressing the fish under heat. A season later, chicks starved on cliffs that had fed them for decades. Seabirds give rapid feedback because they convert ocean variability into chicks or no chicks. In the California current, warm years with thin, low oxygen layers have delivered empty bellies to murres and auklets when krill and young anchovies stayed trapped below the safe band or shifted offshore beyond energy budgets. Die-offs hit headlines, the driver is quiet, layers not aligning. On the seafloor, oxygen loss rearranges gills. Worms and clams that churn sediment and keep it breathable retreat from hypoxic patches. Their absence lets fine particles and organic fluff blanket the bottom, which further suffocates it. Crabs wander into shallower water, where they crowd traps and cannibalize. Demersal fish abandon feeding grounds, concentrating vulnerability. In many estuaries, the first sign is behavioral: shrimp climbing, flounder listing, long before mass mortality. But behavior has costs. Every hour searching for breathable microhabitats is an hour not eating or avoiding predators. Now watch the middle. Forage fish squeeze between heat above and hypoxia below. That strip narrows and predators can corner prey more easily. Catch rates spike, false abundance. Fleets celebrate, then wonder why it collapses the next season. The compression harvests more than intended. Insurance models that assume stable habitat bands can't price a future where the fishable layer slides 100 kilometers in a week. A port that boomed on a predictable run sees boats idle for a month, then scramble on a rumor of oxygen relief after a storm. Economies feel volatility before decline. Buyers expect anchovy for cannery contracts. Instead, a pulse of squid shows up, then vanishes when oxygen dips and squid eggs fail. Restaurants reprint menus, a processing. Plant can't switch its lines fast enough and misses a quarter. Meanwhile, coastal communities with thin margins can't ride out 3 bad seasons in 5. Loans come due on empty holds. Food security rides on these small, fast changes. 3 billion people get protein from the sea. A lattice of local catches, imports, and prices keeps markets balanced when variability is bounded. Break the bounds and whiplash sets in. One year, a glut crashes prices and starves captains. The next, scarcity spikes prices and starves families. Relief programs weren't built for ecosystems where oxygen forecasts now guide where boats sleep. There's a cultural layer here too. Festivals tied to a species' arrival drift out of sync. A community's calendar empties. A reef that sustains small-scale gleaners shifts to turf algae and urchins after fishers take herbivores seeking oxygen refuges in crevices. Kelp forests thin. The canopy no longer buffers pH swings or softens currents. Refuge habitats, seagrass beds, oyster reefs, salt marsh edges become lifelines on hot, breathless nights, but only if they exist. The Jenga metaphor isn't cute, it's apt. Pull out mixing here. Tug down oxygen there, swap diatoms for picoplankton, add a jelly block on top, and the tower still stands, for a while. Then a small nudge, a late storm, a heat wave, a fertilizer pulse, something minor, tips it. You can rebuild, but the pieces aren't the same size anymore. We didn't even stack acidification yet. Lower pH changes, blood chemistry, and shell budgets, tightening the vice on organisms already counting molecules in a thinner band of water. When layers stop talking and the water itself gets harder to breathe, even survivors pay a tax that echoes up the chain. That's the next turn in the story, when low oxygen teams up with falling pH and the invoice comes due in bodies. Acidification's tag team with hypoxia. Now layer in the second stress that rides the same currents. When carbon dioxide dissolves into seawater, it forms carbonic acid. pH falls, carbonate ions decline, and anything that builds a shell, oysters, mussels, pteropods, corals, suddenly pays more to do the same job. It's like asking a marathoner to run uphill while holding their breath. That's acidification. Hypoxia is the breath part. Together, they're not two separate hurdles. They're one long climb where the slope gets steeper with every step. Here's the chemistry loop that links them. Every gram of organic matter that microbes respire strips oxygen and releases CO2 in near lockstep. Low oxygen pools are often high CO2 pools. That means pH is lowest exactly where breathing is hardest, on the bottom of stratified estuaries, within oxygen minimum layers offshore, inside embayments after blooms. The water doesn't just lack air, it turns corrosive to aragonite and calcite. The mineral forms shells depend on. Saturation states drop. Larvae that should sip ions to build their first plates now have to fight the water's tendency to dissolve them back. Physiology doesn't get to pick a stressor. Fish hemoglobin binds oxygen less efficiently as pH drops, the Bohr effect, so the same dissolved oxygen goes less far in acidic water. Heart rates and ventilation go up to compensate, burning more energy in a place that already offers less to eat. Crustaceans juggle acid-base balance in their hemolymph, but buffering takes minerals and time. In low pH and low O2, their aerobic scope, the budget for growth, movement, and reproduction, shrinks. They survive, then stall. Case study, blunt and human. Along the U.S. Pacific Northwest, upwelling now brings to shore deep water that's both low in oxygen and naturally higher in CO2. Add our added CO2, and some summers that intake water crossed a threshold for oyster hatcheries. Spawned larvae in tanks failed en masse. Managers installed sensors and started buffering intake water with sodium carbonate, dosing the sea like antacid. It worked, locally. The fix didn't change the ocean. It bought time inside a pipe. The broader point is the pairing. Hypoxia, sharpened by stratification, acidification sharpened by respiration, both arriving together on a delivery schedule set by winds and currents, and already documented to cause hatchery failures when unbuffered. Out at sea, pteropods, tiny swimming snails, tell the same story with their shells. In waters where aragonite saturation dips, their shells pit and thin. These sea butterflies are snack size for salmon and other fish. Put stress on their shells and you peel calories from the top of the menu. Meanwhile, in low oxygen midwaters, the fish that chase them already run narrow margins. A thin shell is a small detail until it stacks with a hot surface and a breathless layer below. Acidification also tilts the plankton caste. Some phytoplankton groups shift under high CO2, altering community structure and the size spectrum of particles that sink. Fewer large, fast-sinking aggregates means more carbon lingers in the surface to be spired in place, reinforcing low oxygen and high CO2 right where stratification is strongest. That's a feedback. Altered plankton communities change oxygen dynamics, which change pH, which circles back to who thrives. Microstory. A diver slides into a summer bay at dusk. The morning show bubbles streaming from eelgrass leaves, oxygen oversaturation under bright sun. By night, her handheld meter drifts downward. Near the bottom, she tastes the metallic tang of low pH the way some divers swear they can. Crabs crowd a rocky lip at knee depth, antenna, combing the skin of the air water line. She surfaces to hear a hatchery manager on the dock mutter about dosing tanks again before midnight. Managers and fishers now check OATH, ocean acidification and hypoxia, forecasts like weather. Maps that once showed temperature and chlorophyll now add pH and oxygen contours, especially in upwelling systems. The guidance shapes when hatcheries draw water, when fleets set gear in bays that can flip overnight, and when cities open or close storm overflows that would pour nutrients into a system poised to tip. Is the effect always worse together? Not always. Some studies find additive harm. Others see synergy, together worse than the sum. A few species show trade-offs. Low pH hurts, but low oxygen hurts more, or vice versa. The pattern that matters. Co-occurrence is common, where we live and fish, and the pairing pushes more organisms across functional thresholds more often. This tag team isn't theatrical, it's mechanical. CO2 makes the water hang onto fewer carbonate ions. Respiration piles more CO2 where oxygen already runs thin. Physics locks the layers in place. Shell budgets shrink. Blood carries less oxygen. Larvae stumble, and the nightly cycle carves deeper notches. When a heat wave arrives, it doesn't just warm. It amplifies both players. Lower solubility, faster respiration, stronger caps, higher CO2 in the dark. And the invoice shows up at the hatchery, on the deck, and in the market stall the next morning. Tipping points, from low oxygen to no oxygen. To see where this road can lead, we need to go back before there were ports and sensors, back to the moments when the ocean forgot how to breathe. The geologic record keeps receipts in black pages, layers of dark, organic-rich shales laid down when wide swaths of the sea turned anoxic. Oceanic. Anoxic events weren't a single afternoon. They were tens to hundreds of thousands of years when oxygen vanished from huge volumes of water. Life didn't stop, but the cast changed, and a lot of it died. What set those events off? Heat, nutrients, and circulation stalls, familiar words, just stretched across epochs. During parts of the Cretaceous, massive volcanic outpourings loaded CO2 into the sky. The planet warmed. Warmth weakened, mixing. Rain patterns shifted. Nutrient delivery from land and dust rose. Nearshore productivity boomed, sending more organic matter into the interior. Respiration drew oxygen down, while stratification blocked the resupply. The ocean started a slow exhale it couldn't afford. Feedbacks kicked in. As oxygen dwindled, microbial metabolism switched gears, producing chemicals that further reshaped the water, including sulfide in places. That's the rotten egg molecule we met in bays, now painted across basins. Paleontologists can point at ash layers and fossil turnovers and say, this was the moment everything changed. In some events, chalk-forming plankton dwindled, reefs faltered, deep-sea communities collapsed. Black shales piled up because organic matter stopped oxidizing on the way down and got buried. Those shales are literal receipts. Dead stuff, locked away, stacked into the thickness you can measure with a ruler. It took weathering, altered circulation, and new biology to reboot oxygen afterward. The recovery was not a weekend job. Now translate that to today without pretending we're there already. We're not. The modern ocean hasn't flipped to global anoxia, but the ingredients rhyme. We're heating the surface, thickening the lid, nudging winds and currents, and pouring nutrients into shelves. Oxygen minimum zones are spreading. Coastal dead zones recur and grow. We've added acidification to the mix and a faster clock. The plausible picture isn't an overnight planet-wide blackout, it's a patchwork of expanding blackouts regionally. Some seasonal, some sticking around that connect into something bigger than the sum. So what would a tipping point look like in practice? In a semi-enclosed sea like the Baltic, persistent hypoxia already spans decades in places. Add a string of mild winters and nutrient pulses, and the seabed shifts from oxygen-consuming to oxygen-avoiding chemistry. Iron stays locked. Phosphorus leaks back into the water, fueling more blooms, a feedback that keeps oxygen depressed even if inputs drop. That's a local ratchet. Offshore, imagine an oxygen minimum zone shoaling high enough that a major fishery's juvenile layer gets squeezed. into a bath warm enough to hammer survival. Recruitment collapses across a region, not a bay. A season becomes a regime. Another indicator is sulfide flirting with the open ocean. In the past, truly sulfidic midwaters, Euxinia, were a hallmark of anoxic events. We're not seeing that paint across basins now, but early warning would be spikes of reduced compounds in places they didn't belong, hints of sulfide near the core of minimum zones, changes in nitrogen cycling pointing to broader anaerobic pockets. Instrument records would show deoxygenation rates accelerating, not drifting, and contour maps of OMZ depth sliding upward faster than models expected. Microstory. A coring team on a small ship in a quiet gulf pulls up a meter of mud and splits it. The top few centimeters are brown, oxygenated. Below it turns gray, then black, and a faint sulfur smell rises. In the lab they count laminations, thin couplets that say, "No worms mix this." They line up dates and see decades where the bottom went breathless, more summers than not. In the margin, someone draws a little staircase labeled "Stability Lost in Steps." The frightening part isn't just physics and mud. Once interior waters stay low in oxygen long enough, sediments change character. The benthic community shifts to species that don't rework the mud. Internal nutrient loading strengthens. Even if surface inputs drop, the system can resist recovery. A windier year helps. A cold winter helps. But hold the lid thick with heat, and the deck stays stacked. Tipping points in the ocean aren't cliff edges you see coming in a straight line. They're more like surfacing over a threshold and discovering the previous normal requires a run-up you no longer have. Could a global anoxic state happen again? The consensus points to not quickly and not the same. Continental configurations, overturning patterns, and dust supplies differ. But the path to regional, persistent anoxia is open in vulnerable basins, shelves under monsoons that intensify, and upwelling systems that now bring to shore water already primed by low oxygen and high CO2. Stitch enough of those together, and the ocean's capacity to store carbon and ventilate oxygen shifts at planet-relevant scales. The irony bites: lose oxygen, and certain microbes make more nitrous oxide, a strong greenhouse gas which can amplify warming. Early warnings we can measure include the rate of deoxygenation exceeding historical variability, oxygen minima shoaling more than a few meters per decade, increasing frequency of seasonal anoxia in places that used to clear, and chemical fingerprints like rising nitrous oxide or subtle sulfide clues appearing outside of known hotspots. Biological flags show up on decks and docks. Species ranges jumping years ahead of maps, prey fields vanishing across whole cohorts, and fisheries seeing compression abundance followed by empty water. We're not spectators to this. Our chimneys, tailpipes, and river tiles are in the script. Heat thickens the lid, nutrients load the fuse. That's the bridge to the next act, how the human engine writes the oxygen lines we're now reading in the water. The human engine: agriculture, cities, and shipping. Follow the oxygen trail upstream, and it runs into fields, pipes, and hulls. Start in the heartland. Every spring, the Corn Belt loads planters and spreads fertilizer on cold soils. Rains come harder now in bursts. Tiles and ditches designed to move water off fields fast do their job too well, sluicing nitrate straight into creeks, then rivers, then the Gulf. By the time the water turns brackish, it carries a season's worth of growth fuel in invisible form. A June storm over Iowa becomes an August dead zone off Louisiana, paid in diesel by shrimpers who must go farther to find a breathable edge. The pipeline is physical. Drainage tiles cut through loam, miles of perforated plastic that turns soil into a quick-drain sponge. Ditches connect to engineered channels. Levees keep floodplains from swallowing a surge and trickle it out over months. We straighten rivers to protect fields and towns. We also remove the slow filters, wetlands, and backwaters that once turned nitrate into harmless nitrogen gas. On a map, it looks efficient. In the ocean, it looks like a fuse. Policy lives in the middle of that map. Crop insurance rewards maximum acreage. Fertilizer prices and timing push application windows into the riskiest weeks. Ethanol mandates keep corn on a pedestal. Meanwhile, the tools that blunt the runoff, cover crops, prairie strips, restored wetlands, two-stage ditches, exist and work. A county that seeded winter rye across half its acres measured lower nitrate at the outlet the following spring. A farm that set aside 10% for wetlands sent less nitrogen downstream while buffering floods. These aren't silver bullets. There are 1,000 small valves that turn. Microstory. A farmer outside Decatur runs his fingers through rye stubble in March. He used to bare the ground all winter. Now roots hold it. He installed bioreactors, wood chip trenches that denitrify drainage. His yield barely budged. His soil holds more water during drought. His field map shows less red on the runoff index. He doesn't see the Gulf, but he knows he's on its plumbing, and that his choices this week show up as oxygen or no oxygen for shrimpers 2 months from now. Shift to cities. Sewers carry an urban ocean of their own. In many older towns, stormwater and sewage share pipes. A heavy downpour turns treatment plants into triage rooms. Valves open, mixed flows bypass to rivers to keep basements from backing up. Those pulses hit estuaries like a nutrient cannon. Nitrogen, phosphorus, organic carbon, sometimes raw pathogens, all riding out under a summer lid. Even separate systems leak under pressure. Pavement turns a 2-hour soak into a 20-minute surge, and pipes weren't sized for today's rain. Add hotter summers, which speed microbial metabolism in receiving waters, and a city storm becomes a bay's breathless weekend. We have proof that fixes by breathing room. Copenhagen built hard and soft, deep storage tunnels to capture surges, green roofs and parks to slow runoff, real-time controls to meter release. Near home analogs work too. A mid-Atlantic city upgraded one wastewater plant, adding enhanced nutrient removal. Within 2 seasons, dissolved oxygen in the downstream bay rose, algae blooms shrank, and summer fish kills faded. Not gone, not forever, but different. When the lid formed, there was less fuel beneath it. Now look along the shipping lanes. Hulls move the world's goods and stir coastal waters with propellers and wakes. They also bring noise, soot, and chemistry. Heavy fuel oil once delivered sulfur that fell to sea and land. New fuel rules slash that, improving air and reducing acid rain, but also changing aerosol patterns that affect light and iron delivery in some regions. Exhaust still carries nitrogen oxides that deposit to the ocean surface, a small but real nutrient input in busy corridors. Meanwhile, anti-fouling paints leach biocides, designed to stop the slime that slows ships into marinas and shipping approaches where water turns over slowly. Ballast water is a wild card. Ships load it in one port and release it in another, moving plankton, bacteria, and even low oxygen-tolerant species across basins. Regulations require exchange offshore or treatment on board, but compliance varies, and legacy introductions ripple. In some harbors, invasive filter feeders change plankton size structure, clarifying water while routing energy differently. Clearer isn't always healthier. In a stratified embayment, it can mean deeper light penetration, longer daytime oversaturation, followed by a steeper nighttime crash. Then there's the subtle physics of ships at anchor. In congested bays, fleets idle for days in tight grids, their props occasionally churning. In shallow systems, that mixing can locally stir or perversely maintain stratification by shearing layers without breaking them. Add the heat from engines and the shading from dense hull traffic near terminal mouths, and you get microclimates that tilt oxygen budgets. It's small compared to wind and tide, but small stacks. Coastal construction plays into the same equation. Dredging deepens channels, reshaping how salt wedges push into rivers and where dense bottom water settles. Seawalls reflect waves. Marsh removal eliminates surfaces that metabolize nutrients and leak oxygen slowly back into the night. A port expansion that seemed neutral on paper can move the halocline up estuary, placing low oxygen water beneath a nursery flat that used to breathe. The change shows up as a quiet failure in a weak year class, and no one blames a dredge 5 years later. Microstory. A harbor master in a South China seaport taps a monitor that overlays AIS ship tracks with a dissolved oxygen sensor. On windless nights, the map paints yellow along anchor rows. He's not a scientist, but he starts staggering anchorage assignments to spread the impact. Call it small, but a dozen live wells full of fish make it back to dock that week. It's a human patch on a physical problem. All of this circles back to agency. Agriculture, cities, and shipping aren't villains. They're systems we run. Their knobs are visible. Fertilizer timing, tile outlets, wetland acres, combined sewer overflows, tunnel volume, fuel standards, ballast treatment, harbor design. Turn enough of them, and local waters breathe easier under the same warming sky. That buys time and resilience for communities and species learning to live inside thinner bands. Now the harder question, can we scale fixes to match the physics, or are we chasing the tide with cups? The fixes we want versus the physics we have. We keep reaching for tools that feel big enough to fight the sea, and the sea keeps answering with math. Start with the lever everyone names first: emissions cuts. If warming thickens the lid and lowers oxygen solubility, then cooling the future is the only fix that scales with the problem. The catch is time. Even sharp cuts bend the temperature curve across decades, not summers. The ocean's memory is long. Heat already stored in the upper layers won't drain on command. But every tenth of a degree avoided prevents more solubility loss, lessens stratification, and slows the creep of the oxygen minima. It's not optional background, it's the foundation. Below that, nutrient management is the lever that actually moves fast. Precision agriculture trims excess fertilizer by matching application to plant demand. Cover crops hold nitrate in root zones through winter. Prairie strips along contours catch runoff. Wetlands splice the river system back together with slow, denitrifying lungs. We have receipts. In watersheds that deployed these at scale, nitrate at gauges fell, peak flows smoothed, and downstream hypoxia shrank. Limits? Economics and patchiness. If adoption is thin or upstream gains are erased by a few hotspots, the river writes the average. And climate-charged rain bursts can overwhelm good practice, flushing even careful fields. The fix is not one farm. It's a mosaic, guided, and funded long enough to show up at the coast. Cities hold quick wins too. Enhanced nutrient removal at wastewater plants drops nitrogen and phosphorus loads dramatically. Storage tunnels and smart stormwater controls prevent pulses that normally slam estuaries after cloudbursts. Green infrastructure spreads small fixes, curb cuts, rain gardens, permeable alleys that shave the top off urban hydrographs. This buys oxygen on the days that decide a summer, but the physics still counts. If heat waves grow longer and caps stronger, the same nutrient cut yields less benefit than it once did. We're racing moving goalposts. What about pumping oxygen in? Bubble curtains, aerators, and mixers can rescue a cove or revive an inner harbor, especially when paired with nutrient cuts. They break stratification locally, delivering oxygen across a threshold that keeps crabs off pilings and fish in the water column. Port authorities have done this as triage, and it works inside that box. The planet is not a box. The power required to lift the oxygen content of a bay to a sea won't pencil, and the side effects, venting methane from sediments, resuspending contaminants, demand caution and tight engineering. Iron fertilization sits in a different, controversial aisle. The idea is straightforward. Seed iron in high nutrient, low chlorophyll regions, spark a bloom, pull down CO2, and sink more carbon. Trials proved parts of that chain. Blooms did form, some carbon sank, but the system answered with its own complexity. Much of the organic matter recycled in the surface. Oxygen was consumed in place, and export was patchy. Trophic effects rippled. Who eats whom changes when you favor certain phytoplankton. There are legal and ethical knots too. The London Convention put guardrails on ocean fertilization for good reason. Unintended cascades in a system this coupled can be ugly. The ocean's nope isn't a moral stance. It's a warning from feedbacks. Seaweed farms and blue carbon feel gentler, and they can help. Kelp forests and seagrass meadows absorb CO2, buffer pH swings locally, dampen waves, and create pockets of habitat that breathe better at night. Restored marshes process nutrients and store carbon in mud for centuries if left undisturbed. Shellfish farms clear water and can anchor communities. But verification and permanence matter. Torn-up beds return carbon to the water. Warming narrows ranges. Storms erase gains. These are good tools for resilience and co-benefits. They aren't a swap for emissions cuts. We keep looking for a single big hammer because the problem feels planetary. The truth is layered. Planetary leverage, cutting greenhouse gases, sets the ceiling for oxygen futures. Watershed and city leverage, nutrients and flow, set the floor in the places we live and fish. Tech fixes hold the walls in specific rooms when the house shakes. Each has physics-bound limits. You can't bubble your way out of a solubility curve. And the upper ocean has already lost roughly 0.5 to 3.3% of its oxygen since the 1970s. You can't fertilize your way around stratification without paying somewhere down the line. Micro story. A coastal council meets in July with a heat wave forecast pinned on the wall. The wastewater upgrade is 2 years out. The wetland construction starts in fall. The port has a grant for a small oxygenation system in a notorious Back Bay hollow. They vote to stage it now as a safety valve, shift stormwater gates to hold a coming surge in a park basin, and text fleets an oxygen nowcast link. It's not glamorous, it saves a week, There's also a humility we need to write into the plan. Some beloved ideas, like geoengineering the ocean's alkalinity at scale, are being tested in pilot form. They might help the carbon budget, but they'll alter chemistry in ways we'll need to study cautiously, with community consent and hard thresholds to stop if harm shows. The ocean carries our bets far. We shouldn't place them lightly. So what do we actually do this decade? Lock in deep emissions, cuts to slow the lid, blanket watersheds with practical nutrient breaks, retrofit cities so storms don't become hypoxia guns, build and restore blue habitats to earn back local buffers, use oxygenation and mixing as surgical tools, not talismans, and measure relentlessly oxygen, pH, currents, so we can steer in real time. The viral truth is simple and personal. Where you farm, vote, fish, and plug in can decide whether your bay crosses the dawn threshold this summer. Physics writes the rules, but it doesn't write the whole story. We still choose how often we push water past its breathing point. Adapt or gasp, practical paths for people and places. We've named the physics and tested the fixes. Now it's down to how people actually live with thinner oxygen margins. Start on decks at dawn. Fishers can't move the solubility curve, but they can dodge the worst nights. Oxygen forecasts now cast hypoxia like weather. Hourly maps that pair winds, tides, and river flows with real sensors. A captain watching those maps sets nets along the breathable edge instead of guessing, shifts hauling to afternoons when mixing recovers, and leaves certain coves alone on hot, windless nights that always flip. The result isn't perfect, but gear comes back with fish instead of corpses. Managers can match that agility. Static seasonal closures drawn decades ago assume stable layers. Dynamic closures move with oxygen and temperature fronts, opening and closing squares based on live thresholds. It's already happening for whales and bycatch. Oxygen can be added to the rulebook. Pair that with habitat compression accounting. Don't mistake easy catches in squeeze strips for abundance. And quotas stop overshooting during false booms. Gear can breathe too. Traps with escape hatches sized for stressed, slow-moving crabs reduce ghost fishing after hypoxic nights. Deep nets pulled shallower on forecasted low-oxygen days keep catches in survivable layers. On trawls, shorter tow times and larger mesh reduce haul mortality when fish are already taxed. Small changes show up as next-year recruits that didn't die on the deck. Coasts can build refuges. Living shorelines, oyster reefs, marsh edges, seagrass beds do physical work. Slow waves catch sediment and leak oxygen into boundary layers at night. In estuaries with predictable nightly drops, installing baffles that steer currents across eelgrass gives a measurable bump to dawn oxygen in the first meter. Reef restorations raise roughness and surface area, giving crustaceans a breathable microtopography when the bulk water sags. These aren't decorations, they're life support infrastructure. Wetlands are oxygen banks. Reconnected floodplains and restored tidal marshes shave the peaks off nutrient pulses, denitrify trickles that would fuel blooms, and buffer pH swings right where juveniles grow. They also buy minutes on breathless nights, enough to keep gills moving until a breeze arrives. In places that can't rewild whole rivers, even pocket wetlands, 1-acre parcels stitched into ditches, stack into meaningful nutrient cuts. Ports can run triage. Oxygen-poor pockets recur in known back bay hollows. Permanent bubblers are blunt tools, but mobile mixers staged for heat waves can be deployed like fire trucks. Run them for a week in that one basin where fish kills always start, coordinated with tide timing and wastewater holds, and you avert the cascade. It's not a solution, it's a stopgap that saves broodstock and buys faith for longer projects. Aquaculture has to design for the new nights. Tanks and pens need oxygen sensors tied to alarms, backup aeration that starts automatically, and intake schedules that dodge low pH, low oxygen upwelling bursts. Hatcheries and upwelling regions have learned to buffer pH. Many still need to plan for dissolved oxygen drops by staging emergency oxygen cones and diffusers. Site selection shifts too. Pens placed to intersect predictable mixing lanes will ride out heat waves better than those in quiet coves. That map matters now. Food systems widen their palette. Communities that depend on a single species riding a narrow band are brittle. Subsidize processing lines that can switch from anchovy to squid to sardine without retooling for a month. Encourage markets for low oxygen tolerant species, threadfin, some jacks, certain clams, so fleets have options when the usual target sits below a suffocating layer. Culinary shifts aren't cosmetic, they spread risk. Household levers sound small until a storm hits. Cities that pay residents to disconnect downspouts, install rain barrels, and swap lawns for native plantings cut the first flush that turns creeks brown and bays green. Neighborhood-scale bioswales capture bursts that would race through combined sewers. The signal shows up as one fewer bypassed during the exact week a heat wave sets a lid. Policy pressure is a habit, not a headline. Vote and lobby for enhanced nutrient removal at wastewater plants, stormwater tunnels, and wetland bonds. Support farm bills that reward cover crops, prairie strips, and wetland easements, not just yield. Push agencies to publish oxygen and pH forecasts like surf reports, and to write dynamic management into fisheries rules. Funding centers isn't sexy, but no forecast exists without them. Energy choices circle back to the lid. Every kilowatt from wind, solar, or firm clean power avoids heat that would thicken stratification and lower solubility. Coastal communities that build microgrids and cut diesel for port power shrink nitrogen oxide deposition and noise, while hardening against blackouts that could kill aquaculture overnight. Education prepares hands for the new routine. Train deck crews to read oxygen plots and respond to alarms. Teach dock managers to sequence unloading to minimize time fish spend in warm, low oxygen holds. Offer quick courses for wastewater operators on Hypoxia Week's playbooks: when to store, when to release, and how to coordinate with bay mixers and harbor flows. Microstory: a small Gulf town builds a WhatsApp thread with fishers, hatchery staff, the wastewater plant, and a high school science class running a peer sensor. On a Thursday in August, the student posts a dipping oxygen line. The plant delays a release for 6 hours. The port spins up a loaner mixer. Boats lift traps from the worst cove and set them along a breezier point. Friday dawn brings live fish and one more day to the good. That thread becomes a habit, and a playbook other towns can steal. None of this replaces cutting emissions or basin-scale nutrient work. It translates them into mornings and maps. Adaptation isn't surrender. It's how communities breathe through the years it takes the physics to bend. The meaning: our breath has always been borrowed. We like to think oxygen is a right, like gravity, a constant we can't lose. It isn't. It's a gift from photosynthesizers, fronted by microbes that learned to split water and stash the energy of sunlight billions of years ago. We live inside their byproduct. Roughly half of the oxygen in today's atmosphere traces back to the ocean's photosynthesizers. Every lungful is a daily deposit from algae, plants, and especially the ocean's smallest workers, balanced against the withdrawals of everything that breathes and burns. That balance isn't abstract. It's a ledger kept minute by minute in layers of water that only talk when winds, seasons, and chemistry line up. We've spent the last hour walking through the ways that conversation falters: warmth thickening the cap, nutrients lighting short fuse booms, night stealing back the day's gains, acidity pinching shells, and blood. None of those forces care about our schedules. The ocean's exhale is earned, not promised. Humbling, sure, but it's also grounding. If oxygen is a loan, then stewardship is just paying interest on time. Farm choices upstream change, whether a bay wakes up. Breathing. City valves during a storm decide whether a river mouth crosses a dawn threshold. A hatchery's buffering and alarms turn mass loss into hard night. A wetland stitched back into a floodplain holds a pulse long enough for microbes to turn nitrate to nitrogen gas, ending the story before it reaches the tide. These aren't metaphors. They're the hinges the ocean's breath swings on. And there's a longer responsibility we can't dodge. Greenhouse gases are the slow dial that sets the ceiling for how much oxygen the sea can carry and share. Cut them hard, and solubility slips less. Stratification builds slower. Minimum zones creep at a human manageable pace. Stall, and we force oxygen lines to cross living thresholds more often. The difference shows up as a fishery that can adapt versus one that disappears mid-contract, as a lagoon that needs triage 3 nights a year versus 30. Here's the quiet reframe. The invisible threat isn't invisible if you know where to look. It's in the color of a satellite pixel, in an Argo profile's oxygen curve, in a peer sensor that dives after sunset. It's in a farmer's rye stubble, a city's storage tunnel, a port's week-long mixer run, and a hatchery's dosing log. This is not just science, it's civic maintenance for an atmosphere we didn't build. Gratitude helps, strangely. The ocean's breath has always been a collaboration. Cyanobacteria to kelp to mangroves to diatoms, with winds, currents, and minerals playing chorus. We joined late and loud. Now we owe back quiet competence. Fewer nutrients at the wrong time, fewer tons of heat in the sky, more habitat that turns surges into slow release, more sensors so we don't fly blind. Not grand gestures, daily practice. Keep one detail from earlier in mind. Shrinking cells keep carbon near the surface, and stratification keeps oxygen near the surface. That's the plot twist to carry forward. The fix isn't just more algae or more stirring, it's rebalancing who grows when and how layers share. That means giving physics a nudge in our favor. Cooler futures, rougher coasts, slower pulses, and giving biology the room to do the job it's done for eons. So we end where we began, with breath. Your next inhale crossed through trillions of phytoplankton you'll never meet, across a mixing layer you can't see. We can keep that inhale ordinary. We have to choose it. Upstream, on the dock, at the plant, at the ballot, on the grid. One chart, one choice, one breath, then the next. The ocean's breath decides ours. And right now, it's pausing more often in places we depend on. If you want to see how these oxygen lines couple back to climate in a loop that can speed or slow both, watch the next episode on the climate-ocean feedbacks. Subscribe to Freaky Science for true, high-stakes stories that change how you farm, vote, fish, and plug in. Because ordinary choices keep lungs, bays, and futures open.